we will try in this class to complete our discussion of our discussion of conformal field theory, the part that we need for our first pass at understanding the string. Okay, so so just to remind you, what have we discussed so far? We discussed the Virasoro algebra. We've repeatedly used these contour integral techniques. We've discussed the state operator map, and we discussed the constraints and correlation functions from the fact that SL2R annihilates the vacuum, and so is good symmetry of the problem. I gave you a little exercise at the end of the last class, I presume. You've done it, right? This is not a difficult exercise. Okay, this was to constrain the form of 3-point functions. Okay, now in today's class, there are two general things I wanted to talk about before turning to specific theories. The first general thing was about what the fact that T is not a tensor. Okay, so if you remember, we defined primary operators. Okay, so another thing that we defined was a primary operator. We defined a primary operator as something that transforms as follows. So suppose I have O of Z, and we have Z is equal to Z of W. Okay, then O of Z is equal to del Z by, let's see, how it should transform like a derivative. So del Z is equal to del W by del Z dW. Okay, so del del Z by del W, we want it here then, right? Del Z by del W to the power delta or H. What? Ah, thank you. That helps. Okay, thank you. Del this fact, no, this del W by del Z, del W. This is correct. Okay, so let's see. How would we define our primary operator? O of Z went as follows. It transformed the same way as a derivative did to the power H. Okay, so this is equal to, let's just write this, del W by del Z to the power H times O of W. Okay, and W is to be found by inverting the map. Z is a function of W. Or you think of it as a map, W is a function of Z. So let's think of the map, and then this is at W of Z. Okay, so this is how a primary operator transforms. Okay, this operator map was invented to imitate the way a derivative transforms under an analytic coordinate change. And so in particular, it follows immediately that any tensor with n bottom indices, Z, 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 n times, let's call this tensor A, transforms like this, but with weight H is equal to n. Because each of the bottom derivatives picks up one of these factors. And there are n of them. So this is just the usual tensor transformation rule. Tells you that a tensor with n holomorphic bottom indices is of rank H, and if it has n holomorphic and n bar Z bars, okay, then it would be of weight H, which is n, and H bar, which is n bar, because you get another n bar factors of del W bar by del Z bar to the power n bar. You can also define upper and lower indices, exactly. So an upper index has exactly transformation with weight -1, because it transforms with the reverse derivative. Okay, everything's very, what? We don't need, but it might be convenient. There may be an object which naturally, geometrically speaking, is an upper index. So then it will have, if it's like say one upper index with an index Z, it will naturally have, that would be natural way to think of it geometrically, and then this will transform like a tensor of weight -1. Okay? Great. Now, I want to confront this expectation. The things that were tensors transform like primary operators with something that we already know, namely how the stress tensor transforms. Okay? So we already know the transformation of the stress tensor under an infinitesimal coordinate change epsilon of z. The change in the stress tensor, so delta t, is given by the residue of delta t, epsilon of z, t of z with t of w. We just take the residue as z goes to w. Now, had t been primary, this, you remember what how t acted on another primary? You remember that t of z of w was equal to h of w by z minus w, the whole thing squared, plus del o by z minus w plus non-singular. And t behaves exactly like this with h equals 2, which is the number of indices in t. So it behaves like a weight 2 primary, except that there's one additional term. Okay. So clearly under an infinitesimal conformal transformation, this part and this part in t. Okay, so now let's compare this to t of z with t of w, which is equal to c by 2 z minus w, the whole thing to the 4, plus 2t of w by z minus w, the whole squared, plus del t by z minus w, blah, 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 blah. Okay? Clearly, these two terms in the OP reflect the fact that t is trying to transform like a tensor. And had this been 0, t would have transformed exactly like a tensor with 2 indices, like a weight 2 primary operator. But that term is not 0. This means that under conformal transformations, t is not transforming exactly like a weight 2 tensor, a 2-index tensor. Okay. Now you can ask, but how can that be? What about it? Well, you see, what we are doing is a conformal transformation. A conformal transformation is a combination of a Weyl transformation and a diffeomorphism that takes you back to flat space. So always this transformation is in a theory in flat space to another theory in flat space. You see, we're comparing two theories both with the same metric. That's what a conformal transformation does. The metric we're choosing to be flat. Okay? In intermediate steps, you may be going to some non-flat space. We'll talk about that. Okay? But at the moment, yes?
I just want to question that premise over there.
Yes?
It's not clear to me that necessarily everything within the structure will necessarily transform those. Because imagine that any kind of scalar operator that is not primary, and you multiply it by this, right? Then the transformation, it just won't be primary, even though you gave it that structure.
Absolutely. So I should have said more clearly. I should have said that the transformation under diffeomorphisms of a tensor is exactly like the transformations of a primary operator under conformal transformations. Okay? Your point is that it could be that there is a tensor that transforms under conformal transformations, not just under diffeomorphisms, but also under Weyl transformations. In fact, that's going to be what we're going to explain for the stress tensor. So I completely agree with your point. Okay? So let me say what I wanted to say here more clearly again, that the transformation of a primary operator under full conformal transformations of weight h, under full conformal transformations, is exactly the same as the transformation of a tensor with h indices under just diffeomorphisms. You know, under just diffeomorphisms, there's no question that this transforms like this, right? It's formula of diffeomorphism. Is this clear? Okay. Excellent. So now, what we have here is this object here. The stress tensor is going to transform differently. We'll work out exactly how it transforms. But it's going to transform a little differently from the way it transforms under just diffeomorphisms. Now, yes? For if you got it out of the diffeomorphism transformation of a tensor. Our definition of a primary operator was more general. Okay? Of course. Yeah, anyway. Right. Okay, but in the particular case of diffeomorphisms are for integer tensors. Actually, for legal insertions, they will all be integers anyway, or integers up to a constant shift. But forget all that.
So this stress tensor is the same stress tensor that's sourced by the metric?
Yes, it's the stress tensor of the theory. Yes,
Yeah.
sourced by the metric. Okay, so we have this puzzle. The puzzle is that the way T transforms under diffeomorphism is like a 2-index tensor, no doubt about that. Part of the definition of T. Okay? But the way that it transforms under conformal transformations has an additional piece. How can this be consistent? It can only be consistent if, in addition to its transformation under diffeomorphisms, also transforms under wild transformations. So this additional piece must be capturing how T transforms under a wild transformation. Is this clear? Okay? The wild transform that will precisely bring you back to flat space. So that we won't have to worry about covariant derivatives in these arguments, in the final arguments. Is this clear? Okay? Now, so since we know precisely what this OP is, that should be enough to tell us precisely how T transforms under wild transformations.
So you do a very tiny bit of wild transformation, very small, and you don't erase. So you are going to some new metric which has this wild factor sitting in front.
Yes.
Now in this metric, the stress tensor that will be covariantly conserved.
That will be covariantly conserved. That's correct.
One stress tensor.
Yes.
This stress tensor and that stress tensor will be the same or slightly different. You make an infinitesimal wild transformation.
You make an infinitesimal wild transform.
Away from your flat metric.
Correct.
A little bit away.
Yes.
And then in that metric there will be some stress tensor which is covariantly conserved.
Yes.
And will that be the same stress tensor?
Well, we're going to work out. It's going to have an additional shift compared to this. But the covariantness will not be important because that will be like second order effect. Because the shift itself will be first order, and then the derivatives on that. Oh, but you're saying the covariant derivatives on the original metric, on the original stress tensor. Okay, let's just go through the argument to see how it changes. Then we come back to this. Okay, great. So now what we want to do is to take this. Is it clear to everyone that this factor here has the information of how T transforms under wild transformations? Because these two precisely give you the transformations under infinitesimal diffeomorphism. Okay? So let's understand firstly, just algebraically, how it transforms how this term, what transformation this term induces. Okay? What we're supposed to do is to take the residue as z goes to w of this thing, and we keep only this term, because the other two are precisely giving us the tensor transformations. Those are the ones we want. For wild transformation, we're isolating. Okay? So when we do that, we're going to get, well, do you see, we get c by 12 epsilon triple prime of w over z, well, just epsilon triple prime over. So delta t is equal to this. Because we've got z minus w to the 4, we want the pole, so we have to expand the third order in the Taylor series expansion. Third order in the Taylor series expansion has 1 by 3 factorial, which is 6. There's already a half from c by 2, so that makes the 12. C goes along for the ride, so delta t is this. Is this clear? Everyone? Excellent. So this is how T transforms under a diffeomorphism, under this combined diffeomorphism, under the wild transformation. But this was wild transformation by what factor? Well, let's see. You see, when you do a diffeomorphism, okay, you had these, so let's do it carefully. We had,
Exactly the factor that came because of the diffeomorphism cancelled
Exactly. So we have dz bar. Okay, and let us keep track. This t was, this delta t was what? You know, to get the sign right, we have to be a bit careful. So this delta t was what? Let's take a moment here to write. The right formula was that tz z was equal to tww plus delta t, right? Because we had tzz was equal to del w by del z. Let's just check this for a moment. Del w by del z squared tww plus t ww of w of z. This was a finite transformation. Now, which of these gives us? So then this is tzz is equal to okay, tzz is equal to 2 del. So suppose w, suppose we write w of z is equal to z plus epsilon of z. Okay, so that's the infinitesimal coordinate change we're writing. Then this is our infinitesimal coordinate change. Then tzz is equal to epsilon prime 2 epsilon prime tww, so delta t, so tzz is equal to tww plus 2 epsilon prime tww plus del w, sorry? It's because we're doing infinitesimals. So the whole thing is 1 plus epsilon prime raised to the power 2, is take the first step. Right? Okay, plus del w of del w of epsilon of del z del prime epsilon t sorry, that's epsilon del prime t ww. Okay, now this is the quantity that we get from using these terms in the OP. Okay, so this formula epsilon blah blah blah, what it does is when we do the coordinate change, w is equal to w of z plus epsilon of z, our delta t is defined as tzz is equal to tww plus delta t. Okay. With these conventions, delta t is equal to less of t of z, epsilon of z, t of w as z goes to epsilon. Okay, this in principle fixes all factors of minus. No doubt. Okay. As z goes to w. Okay. Now, so let's see. So I'm clearing this. Okay. So now next thing we're going to ask is what is the conformal factor? So that is, suppose we have the original metric was dz bar. Okay. Let's say the original metric was dw bar, because we've written it as w as a function of z. Okay. What is the final metric? Well, the final metric is the same as 1 plus epsilon of z, epsilon prime of z, 1 plus epsilon bar prime of z bar, dz bar. Okay? Let us define this as e to the power phi dz bar. Okay? Phi is going to be an infinitesimal, delta phi, dz bar. So we conclude that delta phi is equal to epsilon prime of z plus epsilon bar prime of z bar, just by exponential. Okay. So now what we want to do is to write this expression here in terms of delta phi. Because under a Weyl transformation, the way you transform depends only on the Weyl factor. So the Weyl factor, the compensating Weyl factor, the compensating, so with the Weyl transformation is the compensating one. You do it with a minus delta phi. Okay? So I'm just going to do it in terms of the delta phi, and then we'll get our final minus sign, which is the most difficult part of this calculation, right at the end. I'll leave that to you. Okay. Okay. So the Weyl transformation here is going to be the compensating one for this factor. So I'm going to write everything here in terms of this delta phi and define as follows. So now this quantity here is clearly, because epsilon and epsilon bar were analytic and anti-analytic, this quantity was simply delta t is equal to c by 12 del z squared delta phi. Because the action of the primes, which were analytic derivatives, annihilates the epsilon bar of z bar. Well, just plug in this delta phi.
Yeah.
This term gives what you want, and this term is 0 because
Yeah.
analytic derivative of an anti-analytic function is 0. Is this clear? Now, that's very nice. That's very nice. We've determined how t, the analytic component of t, okay, transforms under a Weyl transformation. But what we want is, of course, covariant formula. We want to know how all components of t transform under Weyl transform. Okay? So can we covariantize this expression? Well, there are two possible covariantizations. Okay? Could have been the delta t was equal to a t mu nu, del nu of delta phi plus b del squared g mu nu, eta mu nu, delta mu nu, whatever, of delta phi. Both these would work. Okay, in the sense that this will allow us to find will allow us to read off a immediately, because this term, when applied to zz, will give us del z square. This term will give us something else, but it will multiply 0. So our calculation is sensitive to enough to determine a, but not to determine b. Isn't del square part? No, these are two separate tensor structures. Del nu is one two derivative tensor. Del square times g mu nu is another two derivative stress tensor. Okay, these are independent structures. Right? However, now what we're going to use is conservation. The original stress tensor was conserved. Okay. The change in the stress tensor should also, so full stress tensor should be conserved. So, at the moment I'm not going to curved space, I'm just in flat space. I'm doing both things. Okay? So, this quantity had better be conserved. Okay, so let's apply conservation on this. Okay, so we get A times del mu delta phi times del squared delta phi. So I'm just contracting this with the del mu. Okay, plus B times del squared del mu delta phi is equal to 0, which tells us that A has to be equal to minus B. Okay, so conservation tells us that the structure has to be this. But the original part was conserved. That was just transforming like a tensor. I want a minus, thank you. Is this clear? So now once we invoke conservation, basically what we're doing is, anyway, once we invoke conservation, we have enough information to completely determine how the stress tensor has transformed under Wild transformations. Go ahead.
This is the transformation of this tensor under an infinitesimal Wild transformation.
Under an infinitesimal Wild, correct.
Infinitesimal Wild transformation changes your flat space to slightly curved space.
Mm-hmm.
So in the slightly curved space, this is only curved space.
I'm.
Okay, and you impose that hat derivative analysis.
Well, I'm doing the way I was thinking is I'm doing both transformations. I'm doing the diffeomorphism and I'm doing the compensating Wild transformation. So I'm back in flat space. Okay, now this thing has to be conserved in flat space.
Yes, so because the other part is
Automatically conserved.
Or under diffeomorphism, that equation transforms nicely.
Nicely. Basically, it keeps the analytic part analytic and the anti-analytic part anti-analytic.
Yes.
So this is automatic. I haven't thought it through how it would work in flat space, but where once again you'd have to use that the original stress tensor was analytic. How it works outside flat space. Okay, but the result must be true because when you do both, it has to be conserved just in flat space. Okay. Yes.
So if you look at, let's say, the covariant derivative on the curved space,
Yes.
That's going to be the next order.
No, his worry is that the Christoffel symbols will act on the original stress tensor.
On the original stress
Yeah.
tensor, which is different from this one by a little bit.
Yeah, and the way the thing that's going to save you there is that these are not completely arbitrary. It's the point is that this is exactly the Christoffel symbol you would get from doing
This
diffeomorphism.
From doing this while in
Yes, and therefore that will annihilate it. Okay. Yeah, it's clearest to see though if you just do both. Then you just don't have to think about it. Okay, that's the same argument. The same argument because in flat space, how do we know that the transform thing was conserved? Because it remains analytic. Okay, so that will play out there. Okay, great. Other questions or comments? Okay, great. So now we have enough information to read off how the stress tensor changes under Wild transformations because we just read off A, and the rest is fooling around with factors of 2, which is the second most difficult part of the calculation. 2's are difficult, signs are more difficult. Okay, let's try to get at factors of 2 at least, right? Let's see. Okay, so let's see. So, yeah. So, okay. Here, of course, just comparing this, we immediately find that A is C by 12. That's not tough. And now what I want to do is to ask, okay, so I've got this nice, beautiful formula. I want to ask what it implies for the transformation of the trace part of the stress tensor. Okay, and this is what involves delicate factors of 2. Oh, maybe not so delicate. Okay, this nice covariant. I was thinking of it as Z. Okay,
Just
yeah,
one.
yeah. Well, it's easy. So trace T. So suppose I just trace T. Take the trace of T, which is not the same as T Z Z bar. Okay, this is trace T. T mu mu. We'll have to convert that later to T Z Z bar. We'll do that. Trace delta T mu mu is equal to C by 12.
1 minus
Now this becomes delta, del squared. This remains del squared, but this is 2. Okay, so this is minus c by 12 del squared phi. Del squared delta phi. Thank you. Okay, and then if you want, you can convert this to t z z bar. T mu mu is proportional to t z z bar to some factor of t. We won't even worry about that. We'll keep this as a basic formula. Okay? Wonderful. So we found how all of the stress tensor, and in particular, how the trace of the stress tensor transforms under an infinitesimal change, under an infinitesimal Weyl transformation. Okay? That's great. Now, what we need to do is to understand this formula a little bit. See, there's this beautiful fact that if you do a small Weyl transformation, then del squared phi has a nice covariantization. It's R up to some possible factor of 2, which I won't swear by. Okay? And exactly. So if you take the scalar curvature.
And there could have been some terms like del phi squared, but those are given dimension 2.
There could have been terms like del phi squared. There are terms in general.
There are terms, but they will be precisely divided equally 2.
Exactly. We've just found what it is. It's this.
Yes.
Okay. Oh, you mean in the expansion of R? In the expansion of R, yes.
Do one Weyl transformation
Yes.
to the matrix.
Yes, yes.
And ask how R changes.
Yes.
In that change, you will find some del phi squared.
Yes, 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 yes. Yes, 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 yes. Exactly. 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 But, okay. So, but at the moment what we want to do is not even do a transformation. You know, we're just asking, suppose in the original flat space, T mu mu was just 0. Okay? Now, we move to some infinitesimal phi. T mu mu is given by this formula. Now I want to write this formula in a nicer way. Just using the fact that if you evaluate it, if you evaluate R for the metric, take the metric ds squared is equal to eta mu nu times e to the power phi. Just evaluate the scalar curvature on this in 2 dimensions. You will find an answer proportional to del square phi times some number which I cannot remember. Okay? And so with this we find that T mu mu, an alternate way of writing the same equation, is equal to C by 12 times R times some pure number that I cannot remember. If somebody has Polchinski here, they can tell me what that number is. Oh, that's very nice. Thank you very much. Oh, minus C by 12 times R. Okay, so we get this beautiful formula for the stress tensor of a conformal field theory, the trace of the stress tensor of a conformal field theory, okay, at least for a metric that is infinitesimally close to, the to just flat space.
If you integrate both sides on the
Huh? Right hand side is the total derivative, correct? So that will tell you that under integrated, under just like a global scale transformation, now there's no funny transformation. It's only under local transformations that the stress tensor transforms funnily. So this quantity, the quantity that you get by integrating this, okay, would be the generator of scale transformations, global scale transformations. And this would be the statement that that generator is still 0. So the theory is still scale invariant.
Topological issues at the boundary.
Locally you scale things, sure.
Up to
boundary stuff. Let's say that there's a closed manifold. Okay, yeah, exactly. Now if you've got a more complicated genus, you get a particular number. Okay, so I'll tell you that under global scale transformations, you have very simple transformations. Okay, but under local scale transformations, wild transformations, the stress tensor behaves funny. Okay, excellent. So now this formula makes a lot of sense. I want to give you just one quick intuitive way of thinking of the problem. Okay, you see what we've got here is a conformal field theory, and this conformal field theory is very nice. Even quantum mechanically, it is scale invariant. Okay, it's nice and scale invariant, it's conformally invariant in flat space. Okay? Now, what's going on is this. So the trace of the stress tensor in flat space, we know just is 0. We want to know what happens to this trace of the stress tensor out of flat space. When we have this while factor, okay, varying around. You might ask, why are we interested only in a while factor? This is because every metric can locally be made equivalent to this by a diffeomorphism. So if we have the information of how it behaves with the while factor, we have the information completely. And for arbitrary metrics, because up to diffeomorphism you can always bring it locally to the form. Okay? So now what we've got is we're evaluating the trace of the stress tensor. So we're evaluating what the stress tensor does under these local scale transformations in flat space. Out of flat space, in the space with this phi varying around a little bit. Okay? Now, you know, let's say that the theory is such that naive classical manipulations make it while invariant. These naive classical manipulations usually have potential failures with short distance effects involving regulation. Okay? These short distance effects, okay, if phi is constant, we know the theory is while invariant. T is 0, because then it's back to flat space. So these short distance effects can see some derivatives of this phi, because it's short distance. Okay? This expression should be built out of some derivatives of this phi, some generally covariant thing that is dimension 2 and is a scalar. Not much choice. Why not dimension 4, for instance? Well, suppose it had been dimension 4, then it would have to come with a product with cutoff square in the denominator, because engineering dimension of left hand side is 2. Okay? And then you take the limit cutoff to infinity, that would go to 0. Okay? Basically, that's, as you say, there's not much choice. Okay? So it's very natural that you get T mu mu is equal to C by 12 R with some number. I mean, some number times R. This is something you might have anticipated right at the beginning of the calculation. Okay? And our computation here has allowed us to fix that number. Okay? Go on.
2-point function of stress tensor for this number, C.
Yes, the 2-point function sees the number, and that's related to the fact that that R has expansion quadratic in fluctuation. Well, it has linear, but also has quadratic. But go on, maybe tell me what you were saying.
No, let's just let's in slightly higher dimension. If you want to write down, you can write some terms on the right hand.
Yeah. So you see, one way of thinking of this is as follows. T mu mu will be what? See, in higher dimension, let's say you've got an R, let's say in 4 dimensions. You've got something like the Gauss-Bonnet term or something like that. R ABC, R ABC. Okay? That would basically be, you see, one way of thinking of this is as follows.
Can you also operators made out of wild tensors in the higher dimensions?
Correct, the same number of contractions. So the point is the same. See, one way of thinking of this is as follows. Let's take this thing and try to convert it into a correlation function statement in flat space.
Okay. Yes, that's what I want exactly.
Okay? So, you see, suppose I want T mu mu, T, T alpha beta. Suppose I wanted something like this. Okay? What I would do is to take T mu mu in curved space, just a one-point function, differentiate it with respect to the metric, and then set the metric to be flat. Because that differentiation would bring this down. Okay? Because this thing has a term that's linear in the metric.
So you take the one-point function as function of arbitrary metric,
yes,
differentiate it once, and then you set your metric
to be flat.
space.
Okay? Now, that is to say, if this quantity is linear in the metric, linear metric fluctuations,
Yes.
this differentiation after setting to flat space could give you something non-zero.
Yes.
So that's a two-point function.
Yes.
On the other hand, if this quantity is quadratic in metric fluctuations, it's only after two differentiations.
So you will see that this will be in three-point function.
Three-point
In
function.
this example, I
Exactly.
don't know what that is.
Yeah, and as you go higher in high dimensions. Okay. Excellent. And in fact, if you look at Polchinski's proof, which I find extremely roundabout of this, usually when you, this is an exercise I used to do. I don't prepare anymore. Okay, but when I first started preparing this course, I used to do this exercise. I wanted to prove something. I would close Polchinski. I would do it myself. Then I open Polchinski and, okay, he's usually got the better proof. It's not. Here he has very wrong. In this case, I think he has very roundabout proof. Okay. Okay. Okay, fine. Fine. So I'm going to leave it as an exercise for you guys to fix up these numbers. Okay, work this argument through completely, keeping track of all signs using this, and keeping track of all numbers. Okay, you should get exactly the minus c by 12 times r. Okay, now I want to emphasize something. Once you know that this relationship is true, our second structural, though our proof was only for infinitesimal deviations from flat space, our second structural expectation seemed to pin it down to this form. So if we found the coefficient for linear small fluctuations from flat space, we just found it. Okay. So we're going to assume that the form is correct always. Okay, we can prove it more seriously, but I won't try to go there. It's just by compounding these transformations. But I won't try to go there. Okay. Now, if we have something like this, there's something else that one can very easily understand, along the lines of what I was discussing with Indranil, and that is this. Suppose I know the partition function of my conformal field theory in a particular metric. Okay? So suppose I know the partition function of my conformal field theory in a particular metric. Let's say that it was flat space. Let's say that to start with, I know my partition function in some metric, for example, flat space. I know z of eta mu. The question I want to ask is, how do I find the partition, what can I say about the partition function in z of eta mu nu times e to the power 5? This is equal to what?
Differentiated.
Exactly. Exactly. So,
Differentiating the metric with respect to metric brings stress tensor.
exactly. So, exactly as Indranil has intuited, what we're going to do is to take this and ask, well, suppose I change phi by a little bit. Okay. I'm going to try to find a formula that relates z of phi plus delta phi to z of phi. Okay. So, z of e to the power mu nu e to the power phi plus delta phi Okay, so let me abbreviate this notation by just calling it z of phi. That's what z of phi means this. Okay, so z of phi, let's call it this, phi plus delta phi is equal to z of phi times plus z prime of phi, okay, times delta phi. And this is integrated over all space, the two-dimensional space. That z prime is functional derivative with respect to phi at the particular point. So let me write this more seriously. This is del z by del phi of x, delta phi of x, d2x. But now, what is del z by del delta phi? Okay, when we change delta phi, how much have we changed the metric? Delta g mu nu is equal to delta phi times the original metric, eta mu nu times e to the power phi, g mu nu. Okay?
Wasn't the statement of while invariance that this not going to do anything?
No, no, no. So, yeah, exactly. If the theory had been exactly while invariant, it wouldn't do anything. So what we're saying is that theories, conformal field theories, with a non-zero central charge are not completely while invariant. And but the transformation under Weyl transformations is a transformation we can control. Okay? And in fact, that extra term in the stress tensor is precisely that statement. Had it been precisely while invariant, stress tensor would have transformed like a tensor, as you see. So let's just go to the end of this thing and you will see. Okay? So delta g mu nu is delta phi times g mu nu. But now, how does a partition function vary when we change g mu nu by a little bit? By an insertion of the stress tensor. Okay? So delta z, so this thing is z of phi plus del z by delta g mu nu times g mu nu delta phi d2x. Okay? Minus that.
You change the field, you want to compensate by just the metric change.
No, I'm changing the metric. This is the change in the metric. Yeah, no sign. Yeah, but now, again, here you have to be careful to get all your numbers straight. You know, I can't remember how we define delta z by delta g mu nu. So delta z I think we had defined delta z, maybe those are 2 pi, that's what I can talk about. Okay, so if we define some number times square root g times delta g mu nu times t mu nu. This is the change in z. Okay, so we're going to get this delta z by plugging in here. So that's equal to number times square root g, which is e to the power 2 phi, because no, e to the power 5, the square root. Okay, times delta g mu nu, but delta g mu nu was g mu nu times delta phi times t mu nu, using the formula.
That is z times that, right?
Del
Z is a partition function.
Ah, you're absolutely right. You're absolutely right. You're absolutely right. That you're absolutely
Z
right.
times
Was z times this. Absolutely right. Because a correlator, a one-point function, is the path integral inserted with it divided by the path integral. Thank you. So that divided by is this additional z. Thank you. Right. Thank you. Okay. And so this is equal to some number times e to the power phi times, now this is the trace of the stress tensor. So it's c, so everything else is absorbed into the number, times t, but that was r times delta phi. Okay? And now what we need to do is to rewrite this r now for finite phi in terms of phi. Okay? So let's see. How does it go? How does r mu nu scales with homogeneity g to the power 0? Because r mu nu is built out of, can be thought of as built out of products of, for instance, Christoffel symbols, which have homogeneity 0, as many G inverses as G's. Okay? R, on the other hand, is a trace of r mu nu, so it scales like G inverse. Okay? And therefore, this r scales like e to the power minus phi times some derivatives of phi. Okay? So this, the e to the power phi will cancel that e to the power minus phi, and we'll get just some derivative operators on phi. Okay, just basically a del square phi, del square delta phi. Okay? So schematically what you're going to get is something like this. Schematically what you're going to get is integral del squared phi delta phi. Okay? So the variation of the partition function, the fractional variation of the partition function as you explained, is del square phi delta phi. Okay? Now we're going to ask, well, can you think of an object, an expression built out of phi's, whose variation is del square phi delta phi? Del phi square does the job. Okay? So phi del squared phi or del phi squared, same thing. It does the job. Okay? So this quantity with the right number does the job. The number is proportional to c times a number. I'm going to leave it as an exercise for you to work out that number completely precisely. So what we've concluded is that z of e to the eta mu nu times e to the power phi is equal to e to the power number times c times phi del squared phi or del phi the whole thing square. Okay? Times phi del squared phi times phi del squared phi, which is the same as del phi the whole thing squared, integrated over the whole manifold. Okay, now this phi del squared phi applies to this metric eta mu nu times e to the power phi. I told you that once you have the answer for this metric, we have the answer for every metric, because all metrics are connected to this by diffeomorphisms. Okay? But it would be nice to have the explicitly covariant form. Okay? It's not too hard to check that the explicitly covariant form is this. Integral square root g r 1 by del square times r. In the full metric.
Yes.
Okay? Let's just check that that basic features work out right. Okay? For this, this is correct if it reduces to this quantity when I set the metric to be eta times e to the power phi.
Are you not adding r times the del square phi and integrating out something? Then you will get 1 by, like a proper letter.
Well, Yeah, exactly. It's just very simple, as you say. In the case where this thing here, we just have to check that this reduces to that when we set the metric to be diagonal, to be e to the power phi times del square. Then this is generally covariant, so it has to be the right expression. Okay? But we already know what R is. R is equal to e to the power minus phi times del square phi, up to numbers. We know that this is what R is. Now square root g is equal to e to the power phi, and this del squared, this 1 by del squared, because it's contraction with the metric, has an extra homogeneity of e to the power minus phi in the denominator. So the e to the power minus phi is in the denominator, the 2 e to the power minus phi is in the numerator, and the e to the power plus phi in the numerator all cancel with each other. So this becomes del square phi, now flat space del square, 1 by del square phi. See, here was del square in full metric. Here is del squared just in flat space, in the metric eta, okay, which is phi 1 by del square, phi del squared phi.
So you were actually writing the similar kind of term of this phi del square phi in terms of R.
Exactly.
By covariant.
Yes. So I should emphasize here del square is del in flat space metric. Okay? And that expression here covariantizes to this expression. And nothing else, but with a number. You're saying nothing else can covariantize to this expression? Yes, nothing else can, because the proof for that is that every metric can be brought to this form, at least locally.
Okay.
So there's full information. Yes. Yes, Indra? Yeah. Each of these has an e to the power minus phi. Correct? But it's locally cancelled. Each of these has an e to the power minus phi, and then when you contract the dels here, there's an additional e to the power minus phi. And then there's an e to the power phi up here. Del 1 by del square, yes. So, okay. It works. Yeah. Yeah. I'm just saying the homogeneity is correct. Okay. Now, if it does, what can it do? It cannot do anything express other than bring some 2 derivative expression in phi. It will just renormalize this number.
I agree.
Okay. It doesn't. What was the possible problem with homogeneity? There is a leftover factor of e to the power phi. That cannot be.
Del phi square cannot.
What?
Del phi square cannot.
No, it cannot come because it's always yeah, because you can always have this whole thing acting on one side.
Formally you want to write your phi in terms of R, and then you substitute in terms of R.
Yeah.
Which is same as because it's quadratic, add a term like R del square phi and integrate out phi.
Yeah.
Which will give you this expression explicitly, or this is like a program.
Yeah. Let's say this at the infinitesimal. At the
R phi where R is the current.
what?
Some R phi where R acts like some. Yeah, I mean.
Let's say this infinitesimally. It's totally clear. Because infinitesimally R is just del square phi. So R 1 by del square R is del square phi 1 by del square phi. So at least infinitesimally it clearly works.
That's what I was saying.
That's what you were saying.
But
Okay.
simply you just write
Yes.
R times phi and integrate out phi, which will give this.
Which will give this expression. And you can check more seriously that this thing works. Sorry, you were saying something, I guess.
Yeah, I mean, I was saying exactly like we can.
You were saying
current.
Exactly.
So that will be J1 over box J.
Yeah, the only problem with that argument is that that's an infinitesimal argument. Okay, but fine. Once it works infinitesimally, hard to believe it doesn't work finitely. Okay. Okay. So what have we done? What we've done in this class so far is gone from the OP of the T's, read off from that the transformation properties of T under Weyl transformations. From that, then given the fact that from that we concluded that there was a very simple general formula for the trace of the stress tensor as C minus C by 12 times the curvature. Then we turned that into a differential equation to tell us how the partition function of a theory varied as we changed the Weyl factor. And we found that it was non-trivial, but very simple. Why am I saying very simple? I'm saying very simple because it's completely universal. You know, it doesn't depend which theory you're dealing with. It doesn't even depend which manifold you're dealing with locally. Okay, at least in this conformal form, it's a local expression. Okay? It doesn't depend which theory you're dealing with, it doesn't depend. It's just some completely universal thing determined by just one number. So if you know the hard part of computing the thermal partition function. Suppose you wanted to compute the thermal partition function on S times R. Let's say the torus. S times S. That's a complicated object because it has all the information of the spectrum of the theory. There's a great deal of information in that object. We computed this with the metric being flat. Now we compute this same quantity but with the Weyl factor on this metric. All the complicated stuff we've already done. Okay? And then all we have to do is to multiply that with some completely universal geometrical factor that depends just on the Weyl factor and the geometry of the manifold that we are integrating. Okay? So it's nothing complicated, it's just some pure, almost like a geometrical object. Okay? So there's no new information. Okay? There's no new information in the partition function on a manifold and a Weyl related manifold. If you know one, you know the other by a simple factor. Now, this is often how symmetries work in quantum field theory. For instance, Chern-Simon's theory in 2 plus 1 dimensions is classically a topological field theory. If it was genuinely topological, it wouldn't depend on any choice of metric. Okay? Well, it's not genuinely topological in that sense. It depends on the choice of what people call framing. But it depends on the choice of what people call framing in a very simple way. If you know the answer in one framing, to relate it to the answer in the second framing is some very simple phase factors, very similar. Doesn't matter. That'll take us further. Okay? I'm saying, you see, often what happens is that when you've got a theory that is classically has an invariance, quantum mechanically doesn't quite possess that invariance. But it possesses something that's very near to that invariance. One option is that it totally breaks it, like when a quantum field theory develops a beta function. It completely breaks the scale invariance of the classical theory. So 4-dimensional Yang-Mills theory classically is conformally invariant. Scale invariant, conformally invariant. Quantum mechanically 4-dimensional Yang-Mills theory develops a beta function. This is a bad breaking of a classical symmetry by quantum mechanics. By bad I mean that totally changes the physics. There is no sense in which knowing what the behavior is at one scale simply determines what the behavior is at another scale. You have to solve the theory for that. You know, the theory at very high energies is quarks, almost free quarks. The theory at very low energies is protons and mesons and God knows what. And it's very hard to get the physics of protons and mesons from knowing what's happening with this is an unsolved problem. 30, 40 years after the creation of, 50 years after the creation of QCD. Okay? Yeah. I want to contrast this with this kind of breaking of the symmetry. Okay? Here, it's not true that the partition function is independent of the choice of the Weyl factor. But it's almost true in the sense that if you knew it with one choice of Weyl factor, very simply you can calculate it with the second choice of Weyl factor. And this is tightly related to that last term in the TT-OP, as we've seen, as the derivation from today's class showed. Okay? So this is, as I will now show you, this is the best we can do quantum mechanically in building a unitary quantum field theory. there is no such thing as a unitary conformal field theory with C equals 0. See, if C had been 0, then it would have been genuinely violent, because this number here is proportional to C. Okay? But there is no such thing as a unitary conformal field theory with C equals 0. This is what I'm going to show you now. Okay? And so the best we can do if we want to build a unitary conformal field theory, which is sort of while invariant, is to allow it to transform like this. We can't do better.
So is it that if you know the particle very high temperature, you have all temperatures?
No, no, that is not true, because you cannot get from high temperature, well, if you're talking S1 times S1,
Yes.
you cannot go from high temperatures to another temperature by wild transformation. Because, you see,
Scaling only one part of it.
that doesn't work.
Yes.
Scaling one part of it is not a wild transformation.
Therefore that information is still non-trivial.
That information is still non-trivial. And the reason that that is non-trivial is you've got the two length scales. You've got the size of the circle and your temperature.
Yes.
And there's a physical ratio that is unconstrained by scale invariance.
I see.
Okay? This is a much more trivial thing. This is only wild transformations, local wild transformations, which is not as non-trivial as what you want.
So what is it? Like what information is it giving us?
Well, it gives us a lot of information. Okay?
I just want to understand what kind of information I'm looking for. Is it that this card deformation is possible?
No, no, no. Card formula is totally different.
That was totally modular in
Modular inverse, totally different, nothing to do with it.
Modular in use carefully this card deformation.
Yeah. Let me give you one example of a kind of information you get out of it.
Yes, yes.
Okay. Suppose, so this is aside. Suppose you want to compute the 2-point function of a twist operator. So twist operator, which is Zn twist. Okay. So the Zn twist has the feature that when you go around here, you come back to another sheet, and you have to go n times to come back to the same sheet. Okay. In the 2-point function, what you do is you go around. You know, there's a branch cut here. Either this way or this way, you go around. You come back to another sheet. You have to go n times before you come back to the original sheet.
Yes.
Now, if you think about what manifold, say that original theory was on a sphere. You think about what manifold your theory effectively lives on, including the branch cuts. You can convince yourself this is also a sphere. Okay? So, 2-point function with a twist operator is, so now there is some coordinate change that will take you to, how can it be the sphere? You see, the while factor will have to go to infinity or 0 here for this to happen. See, non-contractible loops. There's no non-contractible loops. This thing here can be very small. It's just the Wien's index. Well, with the right while factor, which will be singular.
Okay, right. Right now.
Yes. Okay, you can put this back to being a sphere. So there is a change of coordinates, a while factor, under which this manifold goes to the round sphere. So now if you want to compute this 2-point function,
If you compute the stress tensor and this twist operator OP, then you get the dimension and you get the 2-point function. No?
but no need, something simpler. I'm explaining to you something simpler. Okay, I just want going to compute this 2-point function. But I'm saying this 2-point function is the same as the computation of a partition function on a funny manifold. This n-sheeted thing. Okay? But that object is topologically a sphere with the appropriate while transformation.
The square root z if it is n equal to 2 or something.
Exactly.
That kind of
Exactly. You have to find the right while. So you can go to some standard coordinates. You can write this in these coordinates like metric of the sphere times some funny factor that can be removed by while transformation. So this 2-point function is the partition function of the sphere on this funny space. But the partition function of the sphere is a partition function of the sphere. Let's say it's 1. So all of the answer comes from the funny space. All of the answer for the funny space comes from here. Oh, so that completely determines, for instance, the 2-point function of twist operator.
Okay.
This is one example of use, since you wanted examples.
Yes,
Some examples. But there are many uses of this. I think Advait, haven't you guys worked with this a lot?
Yeah.
So Advait will give you many more examples. It's called the Liouville action.
Yeah, I know the name, but what is it used?
Yeah. Okay. Okay. So let's move on. So what we have done is to understand how these conformal field theories of non-trivial central charge actually transform under wild transformations. All good? Okay. The next general thing I want to say, this is going on forever. Yeah, let's try really try to finish our conformal field theory discussions this class. Is tomorrow a holiday, by the way?
Yes.
Okay, there's no end to holidays. Yeah. The thing, anyway, fine. Yeah. So the next thing that we want to discuss is issues of unitarity. Okay? In order to discuss unitarity, we have to know how the operators that we've been talking about, in particular we will be interested in these ln operators, transform under complex conjugation. Okay? So let us first start in general. Suppose I've got a primary operator phi. I'm going to write out this formula that we write again and again and again. Okay? So we've got phi of z is equal to del w by del phi del z to the power h, and a similar thing for the anti-holomer. Okay? H phi of w of z. This is how operators transform under, primary operators transform under arbitrary conformal transformations. Now, I'm going to apply this transformation to a particular transformation that we discussed, I think, 2 classes ago, namely the transformation that generated the map from the cylinder to the plate. So, suppose we had W is equal to, so suppose we got on the cylinder and we have sigma 1, which is the circle direction, and sigma 2, which is the time direction, and we have W is equal to sigma 1 plus I sigma 2. Okay? And then we said now we take the coordinate z, which is equal to e to the power minus I W. Okay? Minus I W, and does this do the right thing? But yeah, we get sort of minus I sigma 2. So at large sigma 2 it goes to infinity, small sigma 2 goes to the origin. So we had this map, which was the map that took us from the cylinder to the plane. You remember this map, right? Lines of constant sigma 2 are circles. Sigma 1 marks the angle around these circles. As sigma 2 goes to minus infinity, we go to the origin. Sigma 2 goes to plus infinity, we go to infinity. Okay? Now I want to specialize our transformation rule for primary operators to this particular map. Okay, so let's do that. Okay? So I'm going to try to specialize our rule for transformation of primary operators to this map. So let's see. Here we have, because we have z as a function of w, we should do it the other way around. Okay? So phi of w is equal to del z by del w. Phi of w is del z by del w times del z by del w to the power h times phi of z, where this is z as a function of w. Okay. Now let's work it out. Del z by del w is just del z by del w is just z with a factor of minus I. And so we get phi of w is equal to minus I to the power h, z to the power h times phi z of z of 10. Okay, I won't. You know, this is in the theory. This is the operator in the theory with z as the coordinate. This is the operator in the theory with W as the coordinate. So really, if I was a mathematician, I would never write it without that subscript. Okay, but since we're not mathematicians, we all know how to interpret formulas without them being made very explicit. I won't. Okay, I won't. Okay.
Some of these will say coherent orbit of universal group as the next one.
This you can consult Advaita about. Okay. Yeah. Very good. Okay. So now this is the transformation of our field under this particular map. Now let's see. You see, suppose we had an expansion of phi. Suppose phi to start with was an analytic operator. Analytic in the sense that we discussed before in the context of the state operator map. That's analytic everywhere except for possibly the origin, because we want to allow it to be an analytic operator in every state on W. Different states at the beginning correspond to different insertions at Z. So in Z it's analytic only away from 0. Okay? So as we discussed in class, what I mean by this is analytic in the presence of no insertions except possibly an insertion at the origin. And therefore it's analytic everywhere except from 0. Okay? So suppose phi was an analytic operator. It's got an expansion in powers of Z. Okay? It's got some expansion in powers of Z. So phi of Z is equal to, and let me call it phi n by Z to the power n plus h. Suppose I made such an expansion. I put the plus h here, so it will cancel this Z to the power h. Okay? So then this would give us some minus 1 to the power h times sum over n phi n by Z to the power n. But minus I, sorry, I said minus 1, sorry, minus I to the power h times times this. But we're supposed to interpret this formula, remember, by putting what Z is in terms of W. Okay? So in W, what this becomes is this is equal to minus 1 minus I to the power h times sum over n phi n e to the power minus I n W plus, thank you, plus I n W.
Again, I mean, apart from cancelling Z to the H, because phi was what was supposed to be the analytic function.
Right. At the moment, it's just definition, right? I mean, I could redefine my phi n with the chi n, but the rationale will come very soon. Just wait 1 minute. But this phi n and phi minus n will be related by reality. That's the rationale. Okay? So this is, of course, convention, right? It's just names for these coordinates. I could have called these n plus h, but this is a sensible name, as we will see. Makes no difference, because it just cancels. Okay. Now what do we do? We've got this. Now we will take W and remember it was sigma 1 plus I sigma 2. Okay. So in Euclidean space it's just this. And now, perhaps for the first time in our discussion in conformal field theory, we go back to Lorentzian space. We go back to Lorentzian space on the cylinder. So you remember the cylinder was the circle times time. We analytically continue sigma 2 so that sigma 2 becomes time. Now what is the nature of that analytic continuation? Let's see. E to the power minus s for quantum mechanics. Look at the potential part. The potential part is e to the power minus v minus v dt e maps to e to the power is. So I, but s comes with a minus potential. So minus I v dt m. Okay, so the analytic continuation that we always have to make to go from Minkowski to Lorentzian is I t Minkowski is equal to t Euclidean. Right, so that we go from the standard things. Right. So t Euclidean, that which was sigma 2, has to be replaced by I times t Minkowski. Let's call that tau. So we will take sigma 2 and replace it by I times tau. Okay? And so now let's write this out. So phi of w, okay, is equal to this more or less irrelevant factor, but okay, I to the power h. So maybe, just to get rid of this, I'll write this as, anyway, doesn't matter. Fine, leave the I to the power h. Totally irrelevant. And then sum over n, phi n e to the power I n sigma 1. Okay? But now, under this analytic continuation, we have sigma 1 plus I sigma 2. And sigma 2 is I times Tm. So that's sigma 1 minus Tm. Okay? So I times sigma 1 minus Tm. I times, but the I cancels because there was. So now there's no I. Right? Because the whole thing goes to sigma 1 minus T. Okay. What? There's I is outside here. I n times sigma 1 minus T. Okay? Now, suppose phi or minus I to the power h times phi. I should strip off some factor. But suppose up to that stripped off factor, phi was a real field. What would that mean for complex conjugation in this Fourier basis? Well, in this Fourier basis, that just takes in to minus in. And so that, up to absorbing these irritating factors in which I'll ignore, phi n star is equal to phi minus n. Okay, I've said it in the language of classical physics, but as all of you know, in the language of quantum physics, star becomes dagger for the operators. So these operators phi dagger, when we want to impose reality conditions on them, we should impose the condition phi n dagger is equal to phi minus n. Let me emphasize one conceptual thing here. Okay? Let me emphasize one conceptual thing here. When we want to know what dagger conditions we want to impose, it's consistent with computations, that's correct. But something else I want to say. We must always go back to Minkowski space. Minkowski space is where we really want to do physics. Especially if you want to talk about unitarity. There's no unitarity without type. Okay? Minkowski space is where we want to do physics. Euclidean space is a trick. So our reality conditions come from Minkowski space and then give us whatever they give us in Euclidean space. Okay? Now you see that this reality condition, when transferred back, we will usually work. Most of our calculations will be done not in this W plane but in the Z plane. Okay? So the same phi n's appear in the expansion of phi. So we have phi of Z is equal to sum over n, phi n divided by Z to the power n plus h. And with this definition, phi n is minus phi minus n dagger. Now this looks totally strange. Because if you are imposing a complex conjugation in Euclidean space, it looks like it would have related phi n to phi n bar. But that would be totally the wrong thing to do. Because who cares about complex conjugation in Euclidean space? Complex conjugation in Euclidean space is unphysical because there are extra i's compared to Minkowski space. Okay? It's complex conjugation in Minkowski space that we care about. Then we have to translate through what that corresponds to in Euclidean space. That's what we've done. And so if we want to understand these operators and their Hermitian properties, for the primary operators, we must impose the reality conditions phi n dagger is equal to phi minus n. This is very important. Is this clear? Okay, this Upmanyu is why we chose to put this is a real reason we put this n plus h. Because if we didn't put the n plus h, we would have phi n is phi n minus 2h. I mean, that's some, why complicate like that? The other reason, of course, is that n is the frequency of the corresponding state on the sphere. Sorry, on the cylinder. You know, so it's a very physical quantity. Okay, when you go to state language on the cylinder. Is this clear? Okay, great. Now, even though the stress tensor is not a primary operator, the stress tensor transforms by the formula for a primary operator plus an additive shift. I will have, I keep promising you exercises. I will really, tomorrow on the holiday tomorrow, I'll make a problem set and give them to you.
That will be 0 in this particular transformation.
Yeah. In this particular transformation, no, it will be some constant, c by 24 or something.
Yes, yes, like no non-trivial.
No non-trivial dependence on. Yeah, it will be a particular constant.
0 point
Exactly, 0 point energy. Okay, but it's just some constant shift which doesn't change our discussion of reality properties. Okay, so the discussion we had here carries through, even though the stress tensor is technically not primary. For the purposes of this discussion, that doesn't matter. I'll ask you to derive the transformation of the stress tensor under this in a problem set. Okay. Anyway, fine. We'll talk about that later. But for the purpose of this discussion, it doesn't matter. That's why we took t and expanded it as ln divided by z to the power n plus 2, if you remember. Some of you might have been wondering why the plus 2. So it's because t had h equals 2. And that's an example of this general formula. And with this expansion, we have L minus n is equal to Ln dagger. Okay. Now that we understand complex conjugation, we can try to understand constraints from unitarity. Is this clear first? Any questions or comments? Does it, say that again? Ask that again. Can you think of these as creation and these as annihilation? That's what you're asking? Yeah, right. You see, Ln's under L0, let's remember that L0 with Ln was, let's say n is not 0. So the first term doesn't click. So is minus n with a 2. Can somebody remember? Times Ln. No, we just with 1. Minus n. It's m minus n. So 0 minus n times Ln. L0 is on the cylinder the energy operator. For scale invariance on the plane, energy up here. Okay? What this tells you is that Ln carries energy minus n. Okay? So what it tells you is that Ln with a positive n lowers energy, and Ln with a negative n creates energy. Now, particle is a bit tricky. Because for instance, we will see that in terms of an elementary scalar field, these L's will be bilinear in these scalar fields. So if you think of the elementary contour of the scalars to be your particles, then this doesn't create a particle, it creates pairs of particles. But it either releases or lowers energy. That's what's going to be important. Okay. Other questions or comments? Okay. Excellent. So now we want to do a few things. There are various things that I used without proof. There are various things that I used without proof in our derivation of the Virasoro algebra. And I attributed them all to statements about unitarity. So I'll try to remember most of them and try to prove them for you, now that we understand what our commutations relations are, so we can use unitarity. So one of the things I, maybe in the derivation and the discussion around it, one of the things I told you about was that you can prove that the only operator that is annihilated by L minus 1 is the identity operator. Okay. Moreover, well, sorry. Let me prove the following statement. We'll get to proving them all. Let me first prove the following statement. If an operator is annihilated by L minus 1, suppose I've got O is equal to 0, say some phi. There's some state corresponding to the operator phi. L minus 1 annihilates it. Then I'm going to prove, and this is almost 2 minutes, that it has energy 0. That L0 annihilates. This is an operator. The state has energy 0, or the operator corresponding to it has dimension 0. Why is this? It's totally trivial, but let's go through it. Exactly. Let's remember that L1 times, sorry, and I'm saying this for a primary operator, okay? So phi is equal to primary. At least quasi-primary. Okay, so let's remember that L1, L minus 1, L1, L minus 1 was from the Virasoro algebra, was a 2 L0. Okay, now let's take this object here and put it in L1, L1, L minus 1. Because L0 and phi is each. Okay. Now, every quasi-primary operator is annihilated by L1. Okay. So one of the two terms in this commutation relation, though some of you are wondering, have I got my signs right? No, but I have, yeah. So the term with minus in this commutation relation is 0 because L1 is to the right and annihilates phi. So the term with plus is non-zero, which is phi L1, L minus 1 phi, which is equal to 2h phi phi. But this is the same as L minus 1 phi, L minus 1 phi, from the fact that the dagger of L1 is L minus 1. So this is equal to 2h phi phi. And from this statement we derive two things. A, if L minus 1 annihilates an operator, then that operator has to have h equals 0. Okay. B, if an operator has h equals 0, then L minus 1 has to annihilate the operator. Because we're using unitarity here all over the place, because we're using the fact that if the norm of a state is 0, then that state itself is 0. So in that second proof, in the proof where if h is 0, That implies L minus 1 on phi is equal to 0. All we can really say is that if H is 0, then L minus 1 of phi is a state with norm 0. But in the unitary theory, there are no states with norm 0 except the 0 vector.
If I just use this thing that L minus 1, it's this identity there.
What?
L1, L minus 1 is this identity because it's dagger.
I didn't understand. Say that again.
Second line.
This one?
Yeah. That would be just identity.
Why is it an identity? The LL dagger is not in general identity. A dagger is a number operator, for instance, in harmonic oscillator. In general, dagger is not. These are not unitary operators.
Okay, yeah.
Yes.
Yeah, the statement is being made about what happens when each are 0. So what happens to the right hand side when the left one is 0 and vice versa.
Exactly. Exactly. Now, L1 vanishing, okay, L minus 1 vanishing in operator language is del phi is equal to 0. Because L minus 1 was just the derivative operator. Okay? This tells us that if we have an, I'm saying basically obvious things, but anyway, let's just say it. If we have an operator that has H equals 0, then it must be analytic. Sorry, it must be anti-analytic. It must be anti-analytic. It cannot depend on Z. Okay? And if we have an operator with H bar equals 0, then it must be analytic. So analytic and anti-analytic are the same as having 0 weight under the other guy. Okay? This is obvious from many points of view, of course. But it's a clean proof of that. Is this clear? So for instance, in when we looked at the operator TZZ, it was completely analytic and its weight was 2, 0. Okay, the fact that del Z bar annihilated it was not independent of the fact that it had weight 0 under anti-holomorphic slip, under the Z bar transformations. Okay, great, wonderful, excellent. Okay.
Necessarily also primary under anti-holomorphic?
Not necessarily. For instance, you can have an operator that is, that is primary under both and take some Z bar derivatives of it. That will remain holomorphic, primary under holomorphic transformations, but will not be a primary under anti-holomorphic transformations. Okay, so that, yeah, right, not necessary. Okay. Excellent. Now let's prove a few more things. Suppose I've got a primary operator phi with Hn. I'm going to just look at the holomorphic sector identical point here. Okay, so phi is primary with weight H. Okay, now I am going to look at all states. Okay, actually before I start doing this, let me say one or two obvious things, but if you've not heard them before, it's not obvious. Look, what have we got? What these primary operators that we defined in the last class, now let's look at them in terms of creation annihilation stuff. Remember that that a primary operator was an operator such that Ln on phi was equal to 0 for all n greater than 0. Phi was primary if and only if this was true. N greater than 0. L0 is not 0 because that's H.
Yeah.
But all the positive n's annihilated.
Yeah.
But remember, in answer to, I keep forgetting your name. Please say it again. Yankee. I'm so sorry. Okay, so remember the answer to Yankee's question about what these ln's do, whether they're mode creation operators. We'd shown that ln's carry weight minus n. In fact, all phi n's carry weight minus n. If you've got a primary operator phi of weight h, and you expand it as sum over n z to the power n plus h, okay, then you can easily show that this object has L0 phi n is equal to minus n phi n. Let's show it. This is an opportunity to do more contour integral. Okay, remember when we have, fine, I'm just going to use the final result of you remember the result, right? The final result is that if you have two charges built out of contours of currents, okay, you have two charges built out of contours of currents, then this commutator was just a residue of the two currents. So what are the currents that build up let's remind ourselves, what is the current that builds up Lm? Well, remember what? T was equal to sum over n, T of z divided by z to the power n plus 2. So if I want to pull out, Tm, Lm. If I want to pull out Lm, I'll multiply by z and do a contour integral. Z. If I want to pull out T0, L0. If I want to pull out L0, I'll multiply by z and do a contour integral. Okay, more generally, if I want to pull out Lm, I will multiply by z m plus 1 and do a contour integral. Okay, so in this case, the current here is z Tz, first current. The second current was what here? I want to pull out this phi n. So it's z to the power n plus h minus 1 phi n. Phi of z. Those were the two currents. Is this clear? Right? You multiply by the factor such that by Cauchy theorem you will get what you want. Okay. Now I should do one of these as w. And then I should take the pole as z goes to w. But I use the OP. So z w to the n plus h minus 1. Then in the OP I get h phi of w by z minus w the whole thing squared plus del phi by z minus w. Okay. Now I want to see, let's say, what the action of ln on phi n is. So I want to put that second phi n, it's a state, so I want to put it at 0. Okay. So this w was this w was no, I'm sorry. I just wanted the commutator of the. I'm sorry, I said it wrong. I wanted the commutator of two operators so I have to do it at arbitrary. Sorry, it's that contour manipulation. I'm sorry. Just do it at an arbitrary point. I could also. Yeah. Sorry for the last comment. Okay, let's keep going. So what do we get from here? When we do this contour integral, so now firstly we have to get the pole. So this guy just gives us a pole, so that's good. So here we just set z equals w. So we get w to the power n plus h del phi, that's one term. The other term is plus, now we expand, we Taylor expand this. So z minus w plus w, and we take the z minus w part. So we get w n plus h minus 1 times h times phi of w. And then we have to take this and integrate it. So we integrate this del phi is unpleasant, we integrate by parts. So we get minus n plus h plus h. Okay, so the into integral of w to the n plus h minus 1 phi. This was phi n. So we get minus n times phi n. I did it fast and schematically, but you understand? Anyone doesn't understand this, please tell me. These are basic manipulations we keep doing through this course. Okay? So more generally, all phi n's carry energy minus n in an expansion of a primary operator in this way. Okay? Great. So what did I want to say? The first thing I wanted to say was this. I wanted to say that now let me take the state corresponding to the operator phi. Okay, some primary operator may or may not be holomorphic, doesn't matter. Some primary operator, I put it at the center, I get a state by state operator. Okay, now I want to know what I get when I act with this ln on phi. Okay, I know that ln on phi is equal to 0 for n greater than phi. We've shown this. Well, what is the interpretation of that? Ln carries my energy minus n. So it tells me that you cannot use our symmetry generators to lower energy. If you start with a primary operator and you act on it with one of your symmetry generators, that is the ln's, you cannot get a lower energy than the primary operator state. Anything that would have lowered the energy annihilates that state. On the other hand, things that raise the energy, so L minus n's, don't annihilate the state. Okay? Now, all states that are related to each other by action of a symmetry generator, okay, transform in a single representation of the symmetry algebra of your theory. So what do our representations under the conformal algebra look like? The representations are labeled by a state, which is a primary, which is the lowest energy state in that module. This is the Verma module, exactly. Okay? This primary operator is the lowest energy because if you act with any ln's on it, it kills it.
Could you please repeat why ln has energy minus because L0 n is commutator?
It's this argument.
Okay.
Or L0 ln commutator, yes. L0 ln commutator. That's
So phi n, why you are saying that ln phi has energy minus, so what was the statement? I'm sorry.
L0 ln is equal to m minus n.
Yes.
So it's equal to minus n ln.
Yes.
Just that.
Okay.
Okay? That tells you that, that
Right.
ln carries eigenvalue of L0, which is energy, equals minus n. Okay? So, suppose you have a state which by action of symmetry can be lowered, then it's not the primary. Okay? Now, if we were in a physically reasonable theory, then all states in the theory will have there'll be a minimum bound, lower bound of energy. So if you take any state in the theory by acting with L plus n's sufficiently many times, you will get to a state which is annihilated by all L plus n's. Because if that was not the case, then the theory would have energies without a lower bound. Now we are assuming our theory is nice and physically reasonable. Okay? So any state in the theory can by sufficient number of lowerings be brought to a primary state. Okay? The converse of that statement is that every state in the theory can be built by starting with the primary and acting on it with L minus n. Are there many states at the ground state level? Okay. No. In 2 dimensions, well, in 2 dimensions not. Okay. So, all primaries are independent starting point. See, suppose you've got two primaries that are totally see, suppose you had two primaries that had the same energy, but could not be brought to each other by a symmetry transform. Okay? Now, the only symmetry, see, we're looking at the moment, when you look at higher chiral algebras, like Wessel-Witten algebras, then you could have primaries appearing related by, okay? But in our current context, the only symmetry generators that could relate different primaries are L0. The only thing with energy 0. There's different primaries at the same level. And we can always choose to diagonalize L0. How do we know that? From state operator map. So we can work in a basis in which L0 on primary is some definite value. It's part of a definition of primary. Okay, L0 so acts on a primary and keeps you in that primary. Okay? So you start with a single primary here, you act with L minus n, and you get what is called a module, what you call the Verma module. Okay? We talk a bit maybe about null states in 2 minutes. Actually, the Verma module is the thing with the null states. Doesn't matter. But okay, you get some module. Okay? It's like a fan. You've got one state down here, and then the states keep growing as you go higher and higher in energy.
Every primary has their state of
States built on top of it. Okay?
So this forms some irreducible representation
Of the conformal of the Virasoro algebra. Okay? All of these states are related to this primary operator by symmetry. So the whole Hilbert space can be decomposed into a sum over these modules. Okay? So when we first introduced primary operators, somebody asked, why are we making this definition? Was that you? Yeah, okay. Okay. Now we see more motivation. Primary operators are very special from the point of view of representation theory. They label the representations of the Virasoro algebra. Okay? Representations are always infinite dimensional, because there's no end to the number of L's you can act, and there's no end to the number of the index of the L with which you can act. And act with L minus 1 million. It's always infinite dimensional. Very complicated can be complicated if there are null states. Many states can be complicated if there are null states. I'll explain immediately what I mean by null states. Okay, but you get this picture, right? That the whole Hilbert space is decomposed into sums of these modules, each one labeled by a primary operator. So this is how you should think of the Hilbert space of a conformal system. Okay. So now let us study any one particular module. A module built on top of a primary operator of dimension h and perhaps h bar.
If you are doing classical theory of this conformal factor.
Good question. The tensor transformation definition is classical. I think, yes, that is true. I think he wants something more. You know, in higher dimensions, basically primary operators are operators without derivatives. Okay? What you do to go away from primary operators, you act with derivatives. So in higher dimensions, it's very easy to answer the question. You know, the thing itself, the thing that's absolutely local is primary. Okay? The thing that fuzzes out the locality with derivatives is not primary. Okay, that's in higher dimensions how it works classically. Now, here we have more than derivatives. We have these ln's. I would have to think to give you a proper answer. Actually, in ADS-CFT it doesn't matter very much, because the ln's, all they do is put the boundary gravitons. Don't matter very much, but that's large C. So I know, yeah, there's something more to say.
So the representation terms are labeled only by H, right?
Only by H and H bar.
H and H.
Yes. Okay. This, by the way, is a special case of the fact that is a very special case of the fact that conformal representations in higher dimensions, in d dimensions, are labeled by representations of SOD. Here we have 2 dimensions, so we are labeled just by representations of SO2. Sorry, we are labeled by representations of SOD and a scaling dimension. Here we are labeled by representations of SO2 and a scaling dimension. The scaling dimension is the sum of H plus H bar. The SO2 represents which rotations H minus H bar. So that's that special thing. What's interesting though is that this has more structure than the higher dimension case, because it's not just the derivatives. You know, you don't build representations just with L minus 1, which would have been boring. Well, this is what we have in higher dimension. You build representations also with L minus 2 and L minus 3 and L minus 4, which have no analogues in higher dimension. Yes?
If I had some statement acted on it with L minus 1,
Yes.
then that would be the same as having the state with the derivative acting on it, right?
Yes. Yeah.
And wouldn't that increase the weight of H by 1?
Yes.
So you said that the representations are labeled by their weight.
No, by the weight of the primary.
Uh,
Yeah. So the weight increases without bound, as you explained. Okay. But the weight of the primary is what it is. Okay. Fine. So now what I want to do is to study any one of these modules and see what we can say from them. Okay. So the module at dimension at H equal that of the primary is unidimensional. It's made out of the primary. You can act with L0 on the primary, you get back H times that state. You try to act with L minuses and L pluses on it, 0. L minuses will raise the energy. So the lowest energy state in the primary module is H, one state. Now let's look at weight H plus 1. Okay? At weight H plus 1, what's the dimensionality of the primary, of the module? At energy H plus 1? 1. Because you can act with L minus 1 on phi, unique state. Okay? And now what we can do is to compute the norm of this. But that is the exercise we just did here. Right? We computed the norm of the state. So we used commutation relations, and we found that L minus 1 phi, L minus 1 phi was equal to 2H phi phi. Okay? So what we did 10 minutes ago, we concentrated on what happens when H is 0. But now let's look at this equation more structurally. Let's say nothing is 0. Then we get the formula 2H is equal to this divided by this. But both of these are norms, so they're positive. So that tells us that in a unitary theory, all primary operators have to have H positive. And when can they have weight 0? Only if the operator L minus 1 annihilates. Now, L minus 1 annihilating is derivative annihilating. Derivative annihilating means the operator doesn't depend on that coordinate. In particular, the only way an operator can have weight 0, 0, left and right, is if it's independent of space. There's only one operator in a local quantum field theory that's independent of space, the identity operator. So the only operator that can have weight 0, 0 is identity. All operators have to have both H and H bar greater than or equal to 0. You can have H equals 0 and H bar not equal to 0, and then your operator will be anti-analytic.
Could you please repeat the argument once?
Sorry, which argument was this?
For this phi being identity when this annihilates.
Okay. So suppose H and H bar both 0.
Yeah.
Then that tells you that L minus 1 on phi is 0, and L minus 1 bar on phi is also 0.
Yes.
But L minus 1 on phi is del Z on O.
Yes.
L minus 1 is equal to 0 is del Z bar on O. So this operator is completely independent of where you insert it. There's only one operator in a quantum field theory that's completely independent of where you insert it. It's the identity. So the only operator that can have H equal to H bar equal to 0 in a unitary quantum field theory. Where have we used unitarity? We've used constantly the fact that if the norm of a state is 0, then the state is 0. Okay? Only operator in a unitary quantum field theory that can have h is equal to h bar equal to 0 is identity. All operators have h greater than or equal to 0, h bar greater than or equal to 0. If h bar is 0, then the operator has to be analytic. If h bar and h are both 0, the operator has to be both analytic as well as anti-analytic, which means it's identity. Okay? And great. So we've got some information by looking at positivity of norms at level 1, namely energy 1 higher than that of the primary. Now let's try to get information by looking at positivity of norms at level 2. So what is the dimensionality of Hilbert space of the module at level 2?
Physically positive that H cannot be complex.
H cannot be complex. H is an energy. So H is a linear combination of energy and angular momentum. Unitary theory, H is real.
Can you say L0 is we can say that?
Of course, we derive it, right? L0, good. L0 is Hermitian and therefore H is, yes, good argument.
And how this norm also is positive?
It's positive, yes. Cannot be complex. Excellent arguments. Okay. Let's keep going. Now, what do we have? Level 2. So how many states do we have at level 2 in a module?
L minus 1, L minus 2, L minus.
We have 2 states, exactly. So we have got L minus 1 squared phi and L minus 2 phi. Let's call this E. Let's call this state 1 and let's call this state 2. Okay. Now I'm going to create the matrix Mij, which is equal to I. The 2 cross 2 matrix of inner products. I'm going to work it out in a moment, or maybe given time I'll leave it as an exercise for you to work it out. In fact, I'll leave this in it. Let me give you the logic and then I'll leave this in it. Why am I interested in this matrix Mij? I'm interested in this matrix Mij because we have unitary theory. So suppose I've got this matrix Mij and I dot this with alpha j alpha star I. Suppose I take this bilinear, alpha j alpha star I. Okay? This quantity here has to be positive definite because this is equal to the norm of alpha j alpha I. I'll write it this way. Consider the state psi, which is equal to alpha j. Then this quantity is psi sum. Right? Because you just take complex conjugate. No. Therefore, this matrix has to have the property. Exactly. This matrix has to have the property that if you dot it with a vector on the right and the complex conjugate of that vector on the left, in particular if the vector is real, vector times vector, it has to be positive for every possible value of the vector. Okay? Now, the way it's going to work, as you said, is that all the eigenvalues of this matrix have to be positive.
It seems like you're going a little bit in a circle because you defined this by an inner product and then we're saying it satisfies the property containing an inner product.
Yeah, all I'm saying is that it should satisfy this property for arbitrary alpha.
Well, you're defining it as an inner product on the basis element and then saying for arbitrary.
Yeah, not at all surprising that this is true. It's not surprising, but it's useful. Okay, so this quantity here has to be a positive definite matrix, which means that if you dot with alpha on the right and alpha star on the left, for every choice of alpha you have to get, you must get a positive number. Okay? But that's what we get abstractly. But now we can just compute this. How do we compute this? Let me, for instance, compute 2, 2 for you. Suppose we take 2, 2. Okay? This was equal to, now somebody has to remember, m into m square minus 1? Oh, sorry, okay, this, yeah, m into m square minus 1, right? Okay, so this is equal to phi L 2 L minus 2 phi. Right, by definition. But this is the same as phi L2 commutator L minus 2 phi, because the other term annihilates the phi because it's primary. Okay? But now we use the Virasoro relations. Virasoro relations had m into m square minus 1 when these two were equal to each other. So we get 2 into m square, which is 4 minus 1, so 6 times c. 6 times c plus exactly 4 L0. But L0 is h. Okay? And so we see that 2, 2. So what we've derived is that 2, 2 is equal to 6c plus 4h times 0, 0. Zero, 0 is the norm of the primary. Let's take that to be 1 by normalization. Right? So what we've got is the formula then for 2, 2. In the same way you can get a formula for 2, 1. What is the rule? What do you have to do? You know, you will always get something like L2, L minus 1, the whole thing squared, something like that, phi, phi. Now you take the L2 through until it hits the phi. When it hits the phi, you'll get 0. Every time you take it through, you get a commutator. Keep going. Okay? So you'll be able to annihilate, you'll be able to evaluate it in terms of elementary objects. Now the elementary objects that you have to have weight 0. So it will always be L0 or number or constants. So all of these will be some function of C and H. Okay? So exercise. Work out this matrix and prove that positivity tells you in particular that C has to be greater than equals 0. Okay? Strictly greater than 0. That, well, C equals 0 would only be possible if L minus 1 on phi was 0. I mean, there would be no primary operator other than identity allowed in that theory. The trivial theory with no states has C equals 0. We'll have a way out. Okay? Moreover, so this is exercise number 1. Exercise number 2 is find when, you know, there is a bound on the set of C's and H's when you hit a particular wall. You will have a particular state going to 0 now. Find when that wall happens. You know, more generally you'll get you'll get C greater than 0. But you get more conditions. You get more detailed information than that. Okay? You'll get some relationship between C and H has to be greater than obey some inequality. When are those inequalities? Saturated. As anyone who's studied minimal models knows, these saturations are key to solving a large class of conformal field theories. When you have null states. We'll talk more about that next class. Okay, so unless there are questions or comments, we'll stop.
GST perspective, how do you see
gauge theory. What do you mean?
There are two anomalies for usual gauge theories. Now imagine that these were just as a state or
Mm-hmm.
this is a some diffeomorphism is a gauge symmetry.
Mm-hmm. Mm-hmm.
Could it be considered as a truth?
Yeah, maybe. You know, it's not really related to gauge symmetry because diffeomorphism, wine is not diffeomorphism. However, it's probably true. Yeah, you can probably get it. I'm not sure, but you probably can get it from yeah. Yeah, so it's probably true that there's some way of thinking of it in that language. What is the logic for that? Yeah, I think the way you want to think of it is just like a global, let me think. I think you want to think of it like, you know, like you think of it like a global symmetry. Meaning the global symmetry is just scaling uniformly. Okay, so suppose you had just a U1 global symmetry and you scaled it uniformly, you have a genuine global symmetry. Now, you scale it non-uniformly,
That is like gauging the symmetry.
it's like gauging the symmetry, but classically. And then how this transforms under that gauge transformation captures the anomaly of that global symmetry. So I think that's how you should think of it. That you've got this uniform scaling, and then you make it local. Gone.
Derivative of the current
Right.
delta function.
Right.
If you integrate it,
Right.
then you get something finite. Like your t mu is sort of like
Yeah. You could probably think of it in terms of a notha, you know. See, we could introduce a notha, the notha current for this charge we know. Okay, and then we could introduce a current coupling to that, a gauge field coupling to that. I suspect that that would be a way of thinking of this. I haven't thought it through in this language, and I think it's very likely that something like that. So it would be interesting too, and probably all this recent stuff, it's implicit in all this recent stuff.
scaling always puts them in the anomaly polynomial.
Right. Right.
Then he finds out what are the different
Right.
factors that we can write.
Right. It's probably, I'm almost certainly correct. I haven't thought it through in this language. But
Yes, so I didn't see the correct thing I asked you because they are getting it.
We will-
Which is sort of, I understood this is a nice thing for two anomalies.
yeah,
But
right.
This is
Yeah. I think you should just think of it probably like making a global symmetry local, and then think through what the gauge field for that is. I would have to think about it. I'm not 100% sure.
You can rewrite GLD, general relativity as a gauge theory,
But-
by introducing two kinds of connection, one for the translation and one for the rotation, and then imposing the constraint that lowest number of derivatives and Riemann connection. And you can write that kind of gauge theory, like supergravity also.
Right, but you know, it's none of these gauge transformations are wild.
None of them are. That's a different thing.
Yeah,
They are only for power quantities.
that's right. No, there's certainly a way of thinking. I don't immediately know what it is. Yeah. It's an interesting way. I'll try to think through it. Other questions, comments? Okay.